Assalamu alaikum students. Today we are going to study indirect method of FM generation. It will cover CL1 and CL2 while this topic is present in section 5.3 of your textbook. Previously we discussed generation of FM waves through direct method. However, in this lecture we will study generation of FM waves with the help of indirect method. In the direct methods of generation of FM, LC oscillators are used, means those oscillators which are comprised of inductors and capacitors, and there is no usage of crystal oscillators. The LC oscillators are not stable enough for the communication or broadcast purpose. Thus, the direct methods cannot be used for broadcast applications. The alternative method is to use the indirect method, which is also known as Armstrong method. In this method, the FM is obtained through phase modulation, and then a crystal oscillator. Here you can see that a crystal oscillator can be used. Because of this crystal oscillator, the frequency stability is very high, which is basically the main drawback of direct generation. That's why this method is widely used in practice, because this method has high frequency stabilities as compared to direct method. The block diagram for this FM generation by indirect method is shown here. So first study what is written over here. The indirect method was proposed by E.H. Armstrong, so this method is known as the Armstrong method. Okay, fine. And then the next step is, in this method, if we talk about the operation of indirect method, then first we have to generate narrowband FM. Means first we generate narrowband FM, and by modulating the carrier wave with baseband signal, and then the resulting narrowband FM signal is frequency multiplied to obtain wideband FM. It means we will multiply it, we will use frequency multipliers, and because of these frequency multipliers, this narrowband FM will be converted into wideband FM. The purpose of this frequency, this crystal oscillator, is to obtain the required values of frequency deviation, carrier, and modulation index. Okay, the output of the phase modulator is the narrowband frequency modulated signal, which is denoted by SNBFM. So the output of phase modulator we will get a signal which is narrowband FM signal, and thus for sinusoidal modulating signal with the narrowband FM can be written like this. Here we have AC, which is the amplitude of the signal, then we have cos 2 pi f1t, it will be frequency of this FM signal, and then it has phase, which is beta sine 2 pi fmt. Here f1 is basically frequency of the oscillator, and then beta is the modulation index, and since this is narrowband FM signal, so the value of modulation index will be less than 1. Okay, so before going further, we should know that how frequency multiplier works. If at the input of frequency multiplier we have cos theta, then this frequency multiplier will multiply this n with this theta, and at the output of frequency multiplier we will get cos n theta. That's why when narrowband FM is passed through frequency multiplier, we get wideband FM. So this is basically the conclusive or the summary of this whole topic, that first we are producing narrowband FM, and then that narrowband FM will be passing through frequency multiplier, and at the output of frequency multiplier we will get wideband FM. So here you can observe the output of frequency multiplier is basically a signal which is wideband FM, and what will be the form of this signal? It is similar to narrowband FM, and the only difference is that n, which is the multiplier constant, is being multiplied here, So the equation will be AC cos 2 pi n. N is the additional part, and it is showing that now this frequency is multiplying with n, and then we have n beta sine 2 pi fmt. So here nf1 we are representing this nf1 with fc, and beta dash is basically n beta, where now the value of this n beta will be greater than 1, because we know that the beta is the modulation index, and here when it is a narrowband FM, then the value of this modulation index is less than 1. But now when this modulation index will be multiplying with the n, which will be definitely a huge number, so at the output we will get a number which has value greater than 1. So now we can say that the modulation index overall has value greater than 1, and this will be wideband FM signal. So here we are doing an example related to Armstrong indirect method, and I'm hopeful that this will help you to solve all problems related to the Armstrong indirect method. Here you can observe that we have narrowband FM. This narrowband FM is passing through frequency multiplier. After that we are performing some frequency conversion with the help of crystal oscillator, and then frequency multiplier is used again, and at the end we have wideband FM. So what do we want? We are starting with the carrier frequency, which is denoted as FC1, and it is equal to 200 kilohertz, and our frequency deviation is 25 hertz. Now we want to convert these two figures into new figures, which is FC4, which is carrier frequency, and we want it to be 91.2 megahertz, and delta F4, which is frequency deviation, which is equal to 76.8 kilohertz. So the first question arises here is that why we are using two frequency multipliers and frequency conversion module. I mean, why there is a need to use two frequency multipliers? Why are we not using one frequency multiplier, and what is the use of this frequency conversion? So to answer this question, we can start from here, that we want to basically convert this delta F1, which is 25 hertz, into 76.8 kilohertz. So the first question is, how many multipliers do we need? Because we are trying to multiply 25 with some unknown factor so that we may get this 76.8 kilohertz. But interestingly, it is not possible to reach at 76.8 kilohertz, because so we will move around, or we will convert our delta F1 to 75 kilohertz instead of 76.8 kilohertz. So what is the way to find the multipliers, frequency multipliers? We can divide 75 k, which is what do we want, and then divide it with 25, which is the starting point. Then we get to know that basically 3000 multipliers are required if we want to convert 25 hertz into 75 kilohertz. And why we are taking this? Because we are trying to reach close to 76.8, which is not possible if in other case. Okay, so if we use frequency multiplication factor equal to 3000, then 25 hertz will change into 75 kilohertz. But for carrier frequency, interestingly, it will also get changed, because at the start we have carrier frequency equal to 200 kilohertz. If we multiply this 2 kilohertz with 3000, which is basically the frequency multiplier, then we get 600 megahertz, which is not required, which is a huge frequency, and our target carrier frequency was 91.2 megahertz. So the carrier frequency will become 600 megahertz, which is obviously not the required case. So What is the solution of this problem? Because if we are using frequency multipliers, then frequency deviation is not only converting into required result, but on the other hand carrier frequency is also converting, and it will become so huge, which is not the required case. So the solution to this problem is that instead of performing multiplication into one step, we are performing this multiplication in operation into two steps. So we can make we can divide this 3000 into 64 into 48, and we are using these numbers based on nth law consideration. So now what will be the current scenario? First, our carrier frequency and frequency deviation will be multiplied with 64. So n1, which is frequency multiplier 1, we are selecting it 64, and n2 is selecting as 48. So first it will be multiplying, and as a result, when this 200 kHz multiply with 64, we will get new carrier frequency equal to 12.8 megahertz, and the frequency deviation will convert into 1.6 kilohertz. So at this stage we will stop, and then we will pass our signal through frequency conversion, and this frequency converter will only change the carrier frequency. It will adjust its carrier frequency in such a way that at the end of this whole procedure we can get our carrier frequency. So what we can do here, we will perform a crystal oscillator, but the main task here is to decide what will be the frequency of this crystal oscillator. I mean, how can we get this crystal oscillator so that at the end we can get the required results. So now this slide is basically summarizing the whole procedure. Here we are starting with FC1, which is 200 kilohertz, and delta F1, which is 25 hertz. We have decided that our multipliers will be 64 into 48. So after passing through this first multiplier, we are getting FC2, which is equal to 12.8 megahertz, and delta F2 will be equal to 1.6 kilohertz. Now we have to decide the frequency of this crystal oscillator, but we can't calculate it like this. So now we will have to apply operations in reverse order. So before finding this, we have to find FC3 and delta F3. How can we find FC3? We know that FC4 is equal to 91.2 megahertz, and if I multiply this FC3 with 48, then I can get FC4. But now the unknown parameter is FC3. So if FC3 is multiplying with N2 and we are getting FC4, then if we divide FC4 with N2, then we can get FC3. So if I am dividing 91.2 megahertz with 48, then what will be the answer? I will reach at FC3, because now I am moving in reverse order. So FC3 will be 1.9 megahertz, and delta F3 it will remain same before and after frequency conversion. So I know that if before frequency conversion delta F2 is 1.6 kilohertz, so after frequency conversion it will remain same, because frequency conversion will only affect carrier frequency. It will have no effect on delta F or frequency deviation. Now I have calculated FC3 and delta F3 from my previous knowledge. So now the only remaining task is to find this crystal oscillator. I know that before crystal oscillator my carrier frequency was 12.8 megahertz, and after crystal oscillator my frequency is 1.9 megahertz. So if I subtract FC2 from FC3, if I subtract FC3 from FC2, then I get 10.9 megahertz. So it will be the frequency of crystal oscillator. So if I use crystal oscillator of 10.9 If I use 10.9 megahertz, then I can get this frequency which is 1.9 megahertz. So in this way we have calculated 10.9 megahertz frequency for crystal oscillator. So if in this way we can find we have started from FC1 and delta F1, and we have reached at FC4 and delta F4 by correctly selecting the multipliers, which is 64 into 48, and most importantly by selecting crystal oscillator frequency. Okay, thank you, and this is all from Armstrong method, which is indirect method for FM generation.